Okay, I want to create a interpreter for untyped lambda calculus and then try and transform it using defunctionalization into a stack machine. So let's start with a little expression language for untyped lambda calculus. These are untyped lambda calculus terms. We have applications of a term to a term, a lambda from a variable name to a term, and a variable with a name. An example here is the identity function, which is lambda x returns x, and another one, example term. Example is applying identity to identity. Okay, quick check that that compiles. Okay, let's write an interpreter. Okay, so let's make a type for environments. An environment is a mapping from strings to values. What's a value? Well, we don't have any integers or anything in our language, so the only type of value is actually a closure. Let's make value equal a closure. A closure has makes a data type. A closure will have the variable that needs to be applied. It's going to have the term that is going to be in the body, and it's also going to include the environment. Okay, so let's write a naive interpreter. So we have, not exfil, we'll write eval that takes an environment and it takes a term and it's going to return a value. And we're going to do this really naively with no error checking. So an environment, let's do the simple cases first. So if we evaluate a variable I in an environment env, that just means that we look up I in the environment, and of course that's going to return a maybe. So to keep this quick, we'll just say from maybe. Of course, if we were doing this properly, we'd want to actually use some error checking. But I'm just trying to keep things simple here. So if we evaluate a lambda, then we're going to return a closure. And we just package up everything that we know inside the closure. So that's the environment, the variable name, and the body. And if we apply an environment, in an environment we apply f to x, then we need to evaluate f, we need to evaluate x, both in the environment, and then we need to apply those. So how do we apply? Well, applying a closure of a different environment, a body, to a value is just evaluating the body in the extended environment where the variable name maps onto the value. I'll call it val for short. Okay, quick check. Okay, this isn't right. Couldn't match expected value with maybe value to maybe value. From maybe, what did I do wrong here? From maybe, expected type value. Oh, I meant to say from just, of course. Okay, nice and simple. Okay, so if we do a val identity, we get a closure. Couldn't match type term. Right, of course we need an environment. We'll use the empty environment. Couldn't match show value. Okay, so we can derive show here, reload. So we get a closure for identity, and we should get a similar closure for example. Okay. So notice here that when we apply, we have shadowing of the name x here when we apply identity to itself, but that's okay because we shadow the name in the context as well. Okay, so let's rewrite this. It's a val1. We're going to try and step-by-step turn this into a stack machine. Now this is something that's been done in various papers. This isn't really novel, but I tried this today and I thought it was kind of mind-blowing to see how the pieces just fit together. I'd not done it before and I thought it was worth just recording. So Okay, here goes. So the first step that we're going to do is to transform this into continuation passing style. And I'm actually going to just copy this and modify it. Let's move this over here. The type signature is going to change slightly. We'll call this eval1. And I'm going to change this into a continuation passing style, which means it takes a continuation as an argument and returns a result. So each one of these is going to receive a continuation as an argument. The simple cases are just going to call the continuation with the concrete thing they know. But the interesting case is here. So we have multiple recursive calls to eval here. I'm going to change them to eval1. And I'm going to call each one of these and pass them their own continuation. So the first thing I want to do is to evaluate the function. And you'll see what I actually do is I expect this to be a closure. So I'm going to have the continuation take the closure that I expect to be returned here. The next thing that I do is evaluate x. I don't want to turn on block arguments, so let's do this. And here you see this becomes val, so we'll have the continuation take val. And then finally, we're going to evaluate, oh, sorry, that's not quite right. We're going to do this evaluation last. And the continuation is going to be the original continuation here. Okay, I think I got this right. Let's see if I didn't shadow anything. F, X, F, env prime, I, body, env, and X, and val. Okay, so I think we're okay. So let's reload that check. So let's do eval1 of identity in the empty environment, passing the continuation, the identity, and we get the same result. Okay, perfect. So let's just double check with our other example. Of course, in an ideal world, we'd have a little test suite for this, but I don't have one, so I'm just testing in the REPL. Okay, let's extend this a little bit. Okay, so the next step is going to be to use a technique called defunctionalizing the continuation, which you can look up on Google. It's a well-known technique. There was an ICFP talk, I believe, about the concept a few years ago. Okay, the idea is to basically turn this continuation into a data structure. And the way that we do this is to look for the different continuations that we can pass. Here's one continuation, here's a second continuation, and here's a third continuation. And we're going to figure out all of the pieces of data that those continuations close over, and we're going to turn those into a data structure. Okay, so I'm going to call that K of R. We'll make a little type here, K of R. I may get this wrong, we'll see how this goes. Let me extend this a little bit. So let's see if we can do this by, again, copy pasting. I'm just going to change the definitions. This one might take a little bit more care. So the problem here is if we have a K and we don't have an actual continuation, then we need a way to apply a continuation, KR, and turn it into a function from values to R. Okay, that's the semantic interpretation of KR. It's a continuation from values to results. Okay, so for every type of continuation here, we're going to have to interpret it. So one type of continuation here is this one. Okay, so let's capture that as, let's try and give this a name. So this is the continuation when we've just evaluated f. So we'll say we've evaluated a function. And what do we know? So what we're going to do is to move this. We've evaluated function. We're going to have to put some arguments here. We'll figure out what those are. And if we are applying this this continuation, then we'll just copy the body over here. Okay, and it looks like this. And of course, we want to use eval2. So let's see. So now let's see what we need to capture here. We have env prime here, but that's coming from here. We have I and we have body. Let's see what remains. So we have k, we have val, but that's coming from here, and we have env, and we have x. So we need to add all of those things into the defunctionalized representation of this continuation. So what did I say? Env, x, and k. Okay, so env has type env, x has type term, and k is a continuation. So our new type of continuation is a kr. Okay. What about the next one? So we come to eval2. The next continuation is this one. So in this case, we've evaluated the argument. Okay, so let's make a continuation for that one. Evaled argument. And in this case, let's just paste this, evaled argument. And again, we need to figure out what goes here. And we need to be able to apply this thing. Okay, let's bring these back into scope that we had. So we had env, we had x, and we had k. Well, here's the lambda. So let's see, we have val, but we also need I, we need env prime, which I think we can now rename. Well, let's just, for the sake of keeping this simple, we'll not rename that yet. So we need I, we need, we'll do it in the same order. So I, body, and k. Right, so just like before, that's an environment. Now we have a string, a term, and a kr. Okay. And again, we need to paste these over here. So what did I say? N prime, I, body, and k. Okay. And then one final continuation we need is here. So sorry, we need to apply the continuation k here. Okay, one that we're missing, if we compile this, hopefully, oh, okay, I've messed this up. Let's see, eval 50. Okay, that should be an eval 2. That's nice and simple. And value to r with type kr, line 44. That also should be an eval 2, so that's nice and straightforward. Okay, the problem comes when we try to do an eval 2, for example, in the empty environment for the identity function. Now we need a k to pass, and we don't have any way to actually run this. If I was using the old model with eval 1, I would just use the identity function. So I need the analogous continuation, which I'll call done. That's just going to be a function from value to r. Okay, and to apply this, so if we're done with an actual continuation, then we'll just apply the final continuation to the value. And now I can run eval2 on the empty environment with example or identity, and I can pass done identity and get the same result. So that's very good. Okay, this is going to change slightly, so I'm going to rename this to apply to. That's eval2, apply to, and we'll just break this down a little bit like that. Let's see if it reloads. Okay, very good. So the next stage, actually I'm going to call this K2 as well, because this is going to change. So let's do that. No K in scope. K2 is here. Okay, so now what I want to do is try and rearrange this data structure a bit. And in my tweet I said I call this making a stack. So I'm going to copy this. I'm going to put a little line break here. I'll put a line break here. Okay. Now all my 2s are going to become 3s. Okay. So what I want to notice here is that this basically looks like a funny representation of a stack. Okay. So I have at any given point when I'm constructing one of these things, either I'm done, or I have something at the head which is either an eval function or an eval argument, and a tail that is the next continuation. So I have a stack of these at each point in the stack I have one of these two types of things, and then I have done at the end. So what I want to try to do is rearrange this step by step. So let's see, we can comment this first. So my first step is going to be to say K3 is a pair of a continuation that's going to be my final continuation and an actual stack. And my two combinations here are, well, my two options are either an env and a term, or an env and a string and a term. So in any case I have an m, so I'll just push that outside the either. So now I either have a term, or a string and a term. Okay, and obviously none of this is going to build, but we can just sort of map all of this over. Okay, so let's see. If I apply the continuation, this can stay the same as it is today. If I want to, let's see, so if I have, okay, we need to go step by step here. So if we have continuation and a stack, then I want to run this in, I want to add, so we have env and x here, that's the left option, so we're going to add env and left x, oops, to my stack. Okay, so same thing here. If I have well, done is going to be represented by an empty list. So if we have k and an empty stack, then we apply the k. And to pattern match on eval function, that's like saying that we have k and env and left x on the top of the stack. And here we have k and env and the right of, I guess I call it env prime, we can clean this up later, right of I body. Okay, and here, let's see, so what am I doing with the stack here? So here I'm pushing back on eval argument. Okay, so in this case the continuation and stack pair becomes, oops, let's make sure we get this right, env prime and right I comma body pushed onto the stack. So what we've done here is, did I get this right? Let's see. There we go. Whoops. Yeah. So what we've done basically here is to take the left x, this option, to say that we're currently waiting on an argument, take that off the stack, keep the rest of the stack the same, and push a right I body to say that we've actually evaluated the function and we've now evaluated the argument too. Okay. The next case here is, let's see, so my continuation also needs a stack, and if I remember right, that means, oops, I missed off the stack here, didn't I? We can just peel off because I was just using k, I peel off the right I body, and I keep the rest of the stack here. Did I do this correctly? Looks like I did. Not in scope value R, 65. Oh, of course, yeah, I missed the type argument there. Let's see what else. 78 has a problem. Couldn't match type. Stack frame with either. Okay. Obviously I've missed something here. Okay, this is just a parentheses problem, I guess. No, not correct. Let's try to group this correctly. Okay, there we go. So let's do the usual test. So instead of eval2, I'm going to use eval3. Now, of course, I don't have done. What I have is a tuple and a stack, and I get the right answer. This probably isn't the best test in the world, and I could do it some more, but I can write some more at the end. Okay, so the next step is going to be, well, actually, I want to change this. I do want to change this around just a little bit, so just maybe give some better names. So let's actually call this a stack. we'll say type stack is a list of environments, and this bit bothers me that this has such a this is sort of nameless representation, so I'm going to call this a frame. This is basically a stack frame, and a stack frame is, we can reuse our old names. Here we go. We've evaled a function. Well, I guess my currently calling everything 3, so let's do that. Stack 3 and frame 3, and these are going to need a name too. The M has been moved out, and the K3 tail has been moved out too. Okay, so now we can just start renaming a few things. So let's see, K3 is fine. So instead of left, now we're going to call that eval function 3. Instead of right, we're going to use this one. That's in those two places, but also we need to get rid of tuple. Let's try reloading. Okay, so that looks good. Okay, so let's look at the state we're in. We have an environment, a term, a K3R, which is a continuation, and a stack. So let's make one more change on this. I just want to untuple this K3R type. We're actually just going to pass these in directly. So now we have a value to R and a stack. Those were the two things that we had. Okay. So now we have st, and we have k. We have to pass both of these two in this case. So again, we're going to have a stack, and we're going to have a value to R. Okay. So these got commuted around. So there's my stack, and there is my continuation. I think I messed that up a little bit. Let's see, where's the end of that? Okay. I think that's what I want. And the same thing there. Okay, so going back here, so then we had stack was the first argument, and then here this is the new stack, and this is the continuation. Hopefully I got this right. No, not quite. Not in, oh, stack 3, of course. Yep, fine. Couldn't match type. I'm like 79. Yep, there's another one. So stack k, reload, 77. There's another one. Okay, a little check again. Whoops. Right. Okay. So the next thing that we can notice, I'm going to just copy all this over to version 4. The next thing that we notice is that we're back in continuation passing style here. Okay, but let's look at the continuation. So k is the continuation here. K gets threaded through at every point. Every time we see k, k is unmodified. K, there's another k, unmodified. Here's k, unmodified. K is unmodified here, unmodified here. Okay, so k actually isn't used at all. And we're eventually going to just pass in the identity continuation when we run this thing. So let's just erase this. There's no need for this continuation anymore. Okay, and if we apply the identity, the type we're going to get back is just a value. Okay, same thing here. So we're going to pass in the identity continuation, and what we're going to get back is a value. So now we have a function from stacks to values to values. Okay, let's just erase the case. As I said, we're going to use the identity, so I erase the k here because identity applied to value is value. When we apply here, we Just remove the k because it's unmodified. Okay, so there's eval and apply for. So let's apply eval for, and now we don't need the final continuation. We have the right answer. Okay, so let's look at what we've gotten to. We have a stack. A stack is a collection of environments and frames. A frame is that we've either evaluated a function or evaluated an argument. Evaluation takes an environment, a term, a stack, and returns a value. And we have this auxiliary function which called apply, which takes a stack, which is a little cryptic maybe, that takes a stack, a value, and returns a value. It's not 100% clear what this function is doing, but we know it's correct because we've gotten here by refactoring. Okay, but let's look at each one of these functions. So notice everything is tail recursive now. So we've actually turned this into a stack machine. You could actually write this as a while loop that keeps a triple of environment, terms, and stacks, and at each point just either completes with the final value or just modifies one or more of those three things. And that machine is just going to proceed in that while loop by changing its state until it gets to a final state where finally the stack is empty and we return the final value. Okay, so here see eval for calls apply for as a tail call. Eval for calls apply for as a tail call, calls itself as a tail call, and the same for apply. There's no recursive calls here that are not tail recursive. Every single one is a tail recursive call, so we've succeeded in turning this into a stack machine. So to summarize what we did, we CPS'd the original function, giving us this. We introduced a stack by defunctionalizing the continuations, and then we actually turned this into a stack data type by just doing a little type arithmetic. And then finally, we noticed that the CPS conversion was no longer necessary, and we un-CPS'd and turned this into a direct style. That was a tail recursive function. So it's been brought to my attention that there are some papers that take a very similar approach. The Twitter thread has some links in the comments, but I thought this was just so nice how this all sort of slotted together and just worked out so cleanly. So I really wanted to make a video and just show how it works. So hopefully this was useful.